Okay, so firstly, I want to say that on JWST, there are several ways of doing multi-object spectroscopy. So in the near-infrared, you do wide field slitless spectroscopy with both NIRCam and NIRIS, covering the whole of the near-infrared spectrum. But both of these are slitless spectroscopy. So NIRSpec is the only way, and actually the first ever instrument launched into space that can do real multi-object spectroscopy with a slit mask. This is selecting targets, as you know. So this JWebbinar is going to concentrate exclusively on this NIRSpec MOS mode. So just a few details on that MOS mode first. So the NIRSpec MOS mode uses the micro shutter array that's built into the NIRSpec instrument. So this is 250,000 individually commandable shutters so that you can make your own custom slit mask in effect. However, as any of you have put in a proposal for MOS know, that the fact that it's a fixed grid that you can open slits within makes it a very difficult problem for the optimization of your program. However, the nice thing is that then each shutter that you open is tied to a target. So as I'll show in a second, this really helps on the back end for the pipeline reduction of your data. If you want more details on the micro shutter assembly, please go to JDocs with a link on this slide. Then what does the data look like from MOS? So this is an example MOS observation using a prism. So our lowest resolution disperser for the NIRSpec instrument. And as you can see here, those spectra are nicely dispersed as traces across the two detectors we have in NIRSpec. The 4 quadrants of the MSA, so those 250,000 shutters are split into 4 quadrants. They disperse onto the top and bottom of each of the 2 detectors approximately. So 2 quadrants on one detection, 2 on the other for prism. Anyway, for the higher resolution gratings, the traces are much longer across the detector. So then a single shutter in the X direction in this diagram will then fill up the whole detector side to side. We also have some cosmetic issues with the micro shutter array, and that some of the shutters are stuck open. Only a few, we're talking about 20 out of 250,000 shutters are stuck open, but these do give contaminating traces across the detectors, and you can see a few in this real observation here. This is from ground testing data I'm showing here. So during preparation of your MOS observation, you can avoid the areas where these contaminating traces are on the detector. So again, it's all about optimization during planning. And if you want to know more about the properties of the MSA again, and also the expected output of the MSA, please do visit the JDocs for all this information. So then on to a quick overview of the pipeline itself for MOS. So generally the pipeline has 3 stages. So stage 1 takes in the raw detector output. So these are in ramps per integration, what we call level 1B. Stage 1 corrects for all the detector level effects and spits out data products in the count rate image per integration as level 2A. And stage 2 of the pipeline takes those level 2A products. It introduces the WCS calibration and corrects for all the instrumental effects. And then it outputs itself the exposure level calibrated 2D spectra. That's for level 2B data. Stage 3 then takes that exposure level data and combines them from all the exposures. So that's the important thing to note for the MOS pipeline reduction, is that we don't deal with data per exposure or per integration, but per target. So if you put the same target in shutters in multiple exposures, the pipeline will tie all those together as associated targets. So the output from stage 3 is level 3 data, and then a calibrated 2D spectra from all of those exposures that include the target. It also rectifies in the 2D and gives you the 1D extracted. So just in a little more detail for each of those stages, the MOS specific stages. So stage 1 for the MOS is CalWeb Detector 1. It goes through each of the steps listed here. And if you want to know more details on these, please do see the stage 1 notebook of the third JWebbinar. You can find that on the JWebbinar series website. Also, there are additional steps for the alternate MIRI. Then in stage 2, specifically for MOS, we go to CalWeb Spec 2 stage, which goes through all of these different steps listed here. Again, please see the JWebbinar 4 for more details on how this stage looks for all of the spectroscopic modes. And then finally, stage 3 for the MOS goes to CalWeb Spec 3 that goes through these few steps listed here. Again, see JWebbinar 4 for details for stage 3 for all the other spectroscopic modes, and also the different separate stage 3 for the TSO spectroscopy if you're interested in TSOs. So finally, for more information on the pipeline, please do read the documentation for the pipeline. In particular, all these separate pipeline stages are listed in much more detail with each of the steps in more detail as well. And all of the JWebbinar material is, of course, online, where several notebooks went through in more detail on these stages and steps.